Now we'll look at where functions are continuous. So here we have a rational function, and we're asked at what points is the function continuous? Where does the limit equal the value of the function? It might be easier to just rephrase the question and ask us, what's the domain of this? We know that the function can't exist outside its domain, so it won't have a value there. So maybe we rephrase it like that and we ask ourselves, what's the domain of this rational function? And hopefully from your previous studies in math you realize that if there's a denominator, this denominator, which is x plus 2 squared, cannot be equal to 0. So if we find where it is equal to 0, we take those points out. We can find the domain of the function. So first we would take the square root. Square root of both sides means that x plus 2 equals 0, and then solving for x means that x equals negative 2. So everywhere except at negative 2, this function is continuous. That's the domain of the function. We would say negative infinity to negative 2, not negative 2. So we jump over negative 2 with the union, begin again, open bracket, negative 2 to infinity. That's the domain, or where the function is continuous. We can say that a function is continuous on an interval like this, like the domain, if and only if it is continuous at every point in the interval. That means that this function has to be continuous every point, at every place between negative 2 and infinity. It has to be continuous at 0, it has to be continuous at pi, it has to be continuous at the square root of 2. And if it is, if the value equals the limit, then we'd say it's continuous on this interval, also known as the domain. We call a function continuous function if it is continuous at every point on its domain. These are all functions that you've seen so far. Let's name a few. We've just looked at this one that was a rational function. Rational functions are continuous everywhere except at their vertical asymptotes, or holes, which are outside of their domain. So rational functions are continuous functions, continuous on their domains. So are polynomials, so are exponential functions, so are sinusoidal functions. Lots of functions are continuous. Probably most functions that you know are continuous. Now the next point says that we have properties of these continuous functions. If we have two continuous functions, f and g, continuous at a point, then we can combine them and also get like more continuous functions, believe it or not. So we could take two continuous functions and add them together or subtract them together, still get a continuous function. We could multiply them by a constant. Okay, it's constant. Still get a continuous function. We could multiply them together. So two functions times each other are continuous. Two continuous functions as a quotient are continuous as long as the quotient is not 0 in the denominator. As long as the denominator is not 0, the power of a continuous function for an integer power is also continuous. The nth root of a continuous function, still continuous, provided that we can take this root and even the composition of two functions, f of g or g of f, that you might remember, are continuous. So what I think about when I talk about this section all the time is this thing, which you might, just all functions are continuous. Anything you can think about, it's a function, it's continuous on its domain, called a continuous function, and then we combine them and we make more continuous functions. So that's great news for us because the following idea allows us to take limits of continuous functions. So if we have a continuous function g at the point b, and we know the limit of f is b, then we can say that the limit as x approaches c of a composition of functions g of f of x is g of the limit as x approaches c of f of x. This is very powerful, but it seems probably a little bit awkward. What it allows us to do is take this limit statement and slip it inside another function. So again, it's just sort of an extension of what we learned in section 2.2 about evaluating limits by using substitution. What that looks like is here. If we take the limit as t approaches 0 of sine of pi over 2 times cosine of tangent of t. We can let this limit business slip right inside there and take the limit of the tangent of t as t goes to 0, provided these functions are continuous at 0. So sure enough, tangent, cosine, and sine all exist at 0. They're all continuous at 0, continuous functions at x equals 0 because 0 is in the domain of these functions. So we can evaluate the limit as if it was the sine of pi over 2 times the cosine of the tangent of now the limit as t approaches 0 of t. Well, the limit as t approaches 0 of t is 0, so now we have the sine of pi over 2 times the cosine of the tangent of 0. And we've evaluated the limit statement. Now we just have to finish this algebraic expression. The tangent of 0 is 0, so the cosine of 0 is 1. Now we have the sine of pi over 2 times 1, which is the sine of pi over 2, which is 1. So this limit is 1 by basically substitution. So we could do that again. Let's take the limit as x approaches 0 of tangent of pi over 4 times the cosine of the sine of the cube root of x. So all the functions involved, tangent, cosine, sine, and the cube root function have to be continuous at 0. And this is the case. 0 is in the domain of all these functions. If that's true, then we can say that this limit just slips right inside there, and we're going to take the limit as x goes to 0 of the cube root of x, or like even of x, and then take the cube root, which turns this term into 0. So now we have the tangent of pi over 4 times the cosine of the sine of the cube root of 0. Then we just peel it back. The cube root of 0 is 0. The sine of 0 is 0. The cosine of 0 is 1. Then the tangent of pi over 4 is 1. So that kind of looks like this. This thing, the cube root of 0 is 0. So we still have cosine of the sine of 0 times pi over 4, and then take the tangent of that. Then the sine of 0 is 0, so we're going to take the cosine of that 0, multiply it by pi over 4, work backward and take the tangent of that. The cosine of 0 is 1, so now we have the tangent of pi over 4 times 1, which is tangent of pi over 4, and the tangent of pi over 4 is 1. So that limit is also 1. Again, if the functions are all continuous, at that point we let the limit slip in, and then we simply have to peel off the layers and evaluate the algebraic expression.